Okay, so let's look at a rotational kinematics problem. It reads, a ceiling fan is rotating at 0.9 revolutions per second. When turned off, it slows uniformly to a stop in 2.2 minutes. How many revolutions does the fan make in this time? And what are the number of revolutions the fan must make for its speed to decrease from 0.9 revolutions per second to 0.45 revolutions per second? And assuming a constant acceleration in the same one that caused it to stop. So we're just sort of looking at how many revolutions does it make in a chunk of time, right, during that stopping period. All right, so we have that a ceiling fan is rotating, so its current rotational rate is 0.9 revolutions per second. And since I want to know how many revolutions it makes, I don't actually have to convert this time into our normal radians per second, because the kinematic relationships work as long as we're consistent with units, right, in anything in our dimensional analysis. Okay, so this is its initial angular speed, and we know that it comes to a stop. This is the first. Oops. See how much of a habit I am in to do radians per second. We know that it comes to a stop in the amount of time of 2.2 minutes. Now, we do want to pay attention to this unit because our angular speeds our angular velocities are in seconds. So, we know that in 1 minute, there are 60 seconds. And so we have 60 times 2.2, 132 seconds is when this ceiling fan comes to a stop. So the first is, how many revolutions does it make? Well, we also don't know its angular acceleration and the amount of revolutions in this coming to a stop portion of the question. This is part A. Okay, so we want how many revolutions does it make? We want this particular variable. So if we use our kinematics, we know that our change, our displacement, angular displacement, is equal to our initial speed times time plus 1/2 our angular acceleration times our time squared. So our initial angular velocity is 0.9 times 132 plus 1/2, I don't know, times 132 seconds squared. So I need that angular acceleration. This becomes a variable of interest for me. Well, we know that our final angular velocity is equal to our initial angular velocity times our acceleration times time. We have our final, that's 0. Our initial angular velocity is 0.9. Oops, no. Plus 132 times our angular acceleration. So move 0.9 over, negative 0.9 is 132 times our angular acceleration. So 0.9 divided by 132, our angular acceleration is negative 0.0068 rotations per second squared. We've got to keep our units proper. All right, so let's use that up in this relationship. We have 0.9 times 132. So this is equal to 118.8 plus 0.5 times negative 0.0068 times 132 times 132. And that gives us negative 59.24. So 118.8 minus 59.24 gives us the total number of rotations of 59.56 rotations. All right, so in that amount of time, we make 59.5 rotations. All right, part A. Part B says, what are the total number of rotations the fan must make for its speed to decrease from that 0.9 to 0.45, assuming that constant acceleration that we've just determined here. All right, so that's sort of a new problem. So we're going to set up a new list for part B. Our initial angular speed is still 0.9 rotations per second. Our final angular speed, we want to know that 45 rotations per second. So it's going to 45 rotations per second. Our time, well, we don't know, because this is not the same time as that. This is the time just to go between these two angular speeds. But we did determine the angular acceleration of the fan, which is 0.068 rotations per second. And we don't know the change in angular location, so our displacement, angular displacement. This is what we want to know. All right, so we have that kinematics relationship that tells us omega final squared equals omega initial squared plus 2 times a delta theta. And we're interested in that delta theta. So omega final squared, 0.45 squared, is equal to 0.9 squared plus 2 times negative 0.0068 delta theta. I hope that's still on the screen. Sometimes it gets off calibration. So 0.45 squared is 0.2025. 0.9 squared is, I could have done that one in my head, 0.81 minus, it's a minus because we have that negative here, 2 times 0.0068, 0.0136 delta theta. All right, I'm going to bring my 0.81 over. I have 0.2025 minus 0.81. I get negative 0.6075 equals negative 0.0136 delta theta. And I will then divide that by negative 0.0136. And we get 44.67 rotations is equal to delta theta. It's almost 45 rotations. All right. So using our kinematics, like we've been doing with translational motion, we can simply translate to rotational motion. Good job.